for having me here. It's really great to turn it on.
This needs to be switched on. There we go.
Ah,
Great.
perfect. Can you guys hear me okay? It's really great to be here. I am a part of the USF family. My son goes to school here in the data science program, but he's an undergraduate. Um, and you guys have a fantastic program. Um, and also, we have two of your recent graduates from the master's program in data science as a part of our team. I wanted to talk to you about. Um, Originally, Father Paul asked me to do this talk, and I was thinking about what to do. I do have a little bit on Y&I, but that is not the purpose of the talk. The purpose of the talk is to share with you, um, as you embark on your career in data science, some lessons that I have learned. So long before Infosys and long before Y&I and Infosys and SAP, I actually did my PhD in AI at Stanford down the highway. Um, by the way, Dean Jeremy is here from the School of Engineering. He and I both are Stanford graduates, and both of us are in love with USF, so we have this thing in common. The and I have seen the field of AI across 4 decades. This is the fifth decade that just started of my association with AI, and so I thought that as you think about your careers in data science, I'll share with you some lessons. So the way I have organized my talk, how much time do I have? An hour? Okay. Um, Hopefully it will provoke some thoughts in you guys and you'll have some questions for me. I have organized this talk. I'll first share with you some observations about the current state of AI and where things seem to be headed. Um, and then I have, towards the end, 4 specific lessons. Uh, so it seems that we are all living in this time of AI. There have been over the last um, 10 years or so, especially, some really remarkable achievements. I have a smattering of these here. Um, right in the middle is the today's Squad leaderboard. How many of you here are familiar with Squad? Just 3 of you. Squad is the Stanford question answering data set. It's a collection of relatively simple reading comprehension type problems. This is the second version of it. They are different than the typical SAT reading comprehension problems in the sense that the answers to the questions are inside the paragraphs. You don't have to have a general common sense understanding of the world in order to answer the question. Everything is in there. Squad 2.0 is a slightly more sophisticated version of these questions because sometimes there could be negations and things like this. And then the first row that you see up here, this first row is the human performance. They asked 500-600 people on the Amazon Mechanical Turk to answer these questions. And the answer, there are two different tests, this DM test and the F1 test. The answers are whatever that score is, 86 something for the first one and 90 something for the other one. So as you can see, the top 12 or so of these systems are all beating human performance. You can also see that Albert, which is the technique that Google invented, a large neural network. They had invented a large neural network called BERT. How many of you are familiar with BERT? Many of you are familiar with BERT. Good, that's good. Um, about 5 months ago or so, Google updated BERT in a smaller network, more efficient networks, little bit better performance, called Albert. And so most of the techniques that you see are all variants of this Albert network. And basically all the top scorers are beating human performance. You can also see that other than 3 of these 12, all the rest are from China, including the top 3. Um, and there are several other examples. The 3 pioneers of deep learning won the Turing Award, the most recent Turing Award. There's a picture on the left-hand side of facial recognition in real time of a person who is about to shop for something, and so forth. There was a report from DeepMind recently that AI can predict kidney failure 2 days in advance. GE recently got the FDA approval for an AI-powered X-ray system. So there are some really remarkable achievements that AI techniques have been able to get to in the last, let's say, 8 years, 9 years or so. And that has largely happened because of advances in these techniques called deep learning and variants of that, as well as a dramatic expansion in computing power because of Moore's law. The fact that several companies, especially the web companies, you have all grown up in the time of these companies. They have massive amounts of data of live situations that you can train these deep neural networks on. So combination of these things has led to these quite extraordinary achievements. But at the same time, there are some very significant issues. These techniques lead to many variants, many kinds of harmful behavior. In the middle is a picture taken just before that Uber car hit that pedestrian. They looked at what the networks were seeing at that moment. They thought that there was a bicyclist first, and that the bicyclist was going to cross in time. And there was a human driver, the control driver in the car, but the driver was not paying attention. And the car slammed into this person who was pushing a shopping cart. And the thing about neural networks, as powerful as they actually have no idea what a bicycle is, or what a shopping cart is, or what a human is for that matter, or that a human has lives, and if you hit the human, they die, and that is a very bad thing, and that should be avoided. None of these concepts are known to this neural network that we basically hand over the control of the car to. There are some other examples here. In particular, there is this deep fake of some guy transposing the image of Steve Buscemi on Jennifer Lawrence's body, and it's quite creepy to see that. But it is possible to do this kind of thing now, and people mimic the CEO's voice to get very large approvals of illegal things in a very big example of cybercrime recently. And on the left-hand side, there is a picture of bias at a system in one of the large companies. In this particular case, it was Amazon, although one of the US government agencies analyzed, and all the big companies were basically doing the same type of a thing. So this isn't to single out Amazon. In this particular case, there was particularly significant bias for all categories of applicants other than white males, and in particular for African American women, it was something like 10 to 12 times worse. And I read about bias in these systems, and the reality is that these deep neural networks have absolutely no idea. They are just, when you open up a deep neural network, it is a collection of numbers. It has no idea what you are trying to do, or it has no internal representation of a meaning of the world in any sensible way. There are other ways in which issues have showed up. These systems can be fooled quite easily. There was this famous example of a stop sign. When you put some stickers in a particular set of places in the stop sign starts to look like a speed limit sign. Whereas even if a 6-year-old child was to look at a stop sign, even a badly mangled stop sign, they would see that there is a speed limit sign has a white background, not a red background. It is a rectangle, not an octagon. Doesn't have the words STOP in it, and so forth. So there are things that we know about what it means for something to be a stop sign, that we would never confuse a stop sign with a speed limit sign. And there are many other examples of how easy it is to trick an AI into doing something pretty bad. In fact, there was one particular example. It's in the middle on the top here. Radiology is one area where AI can have a particularly dramatic impact. So there are many examples now over the last 2 years of applications of deep neural networks to radiology that led to better than human radiologists' performance. But at the same time, this is from one of the journals of radiology recently. They found that it turned out that in the pictures there were certain markings. So the neural networks were not really settling down on cancer. They were settling down on those markings, and those markings were put there by human doctors who suspected that there was cancer in those particular pictures. So when they randomly distributed these markings across the pictures, the accuracy of the thing dropped to 45%. Of course, because again, the same point that the network doesn't actually know what a marking is versus what a cancer is. Um, and there are many other, some funny examples here. Janelle Shane is a particularly funny researcher. She collects these examples of these systems doing stupid things. In the middle, there is a very nice paper that you might want to check out called The Elephant in the Room, where they literally introduce an elephant's picture into a living room's picture, and then it throws off the recognition of the network. Even though it recognizes that there is an elephant, and anyone looking at this picture, any one of us looking at this picture would be like, how did the elephant get into the room? The room is in fact smaller than the size of the elephant, etc. So there are all these limitations, and yet there are tremendous applications. Um, I tried to put all the venture-funded AI companies that I could find on one slide, and this is the situation. The big box on the left is the American venture-funded companies, and this box on the right is the Chinese ones. The people are basically applying these techniques to every walk of life, every industry, every kind of a situation that you can imagine. And there is insane amounts of investment that is going in. 2019 alone, one estimate was that it was more than $25 billion in venture capital investment. Very quickly, the other thing that we hear about is with regard to automation. There is a lot of analysis of the impact of AI on jobs. I used to run a large company called Infosys, which had more than 200,000 employees. And everybody used to ask us, what is the impact of AI on jobs and so forth. And you hear Li Kai-fu is one of the famous venture capitalists in China. He had this estimate that more than half of the jobs that we currently have in the world will be destroyed by AI. There are many other studies of this. In fact, the McKinsey guys did a even deeper analysis of which jobs are likely to go first and so forth. So this is one very real prospect that we are all facing, is that the jobs paradigm that we have right now is at threat because of the power of these techniques. And this is the reality that all of you will enter into the workforce. So I covered a very, very large amount of ground very quickly because I want to get to what is going on here. I started studying AI, what used to be called AI back then, back in the 1980s. I got my PhD in the middle of 90s. And I think that what is going on, John McCarthy, who was the father of AI, who in fact came up with the phrase artificial intelligence, he and Marvin Minsky organized a workshop in the summer of 1956, which created the field of AI. John was the head of my qualifying exam committee. He saw back in 1984 or 1985, when backpropagation was invented, which really broke open the field of neural networks. At the time when I started studying AI, neural networks weren't even considered a part of mainstream AI. And already we saw that in perception kinds of applications, neural networks were quite powerful. And so he wrote a beautiful paper, which was called Machine Learning Should Focus not on the appearance, but on the reality behind the appearance. In fact, I skimmed over one particular picture that I wanted to show you. Sorry. It was something that I took, and so I think I should mention that. So on the left, you see a picture of the Singapore skyline. And I was there year and a half ago or so. And I woke up in the morning, I was looking at the skyline, and all of a sudden this orange glow showed up in many buildings. And it was mystifying for a second. What's going on here? And then it took me a couple of seconds to realize that the sun was coming up on the other side. I couldn't see the sun because it was hidden behind these buildings. But obviously it was the sun coming up, and there was this beautiful reflection of the sun on all of these buildings. And until you understand that there is sun coming up behind you, and there is such a thing as the sun, it goes up, and as it comes up, it reflects this light and so forth. There is an underlying phenomenon that is causing the thing that you're looking at. Yes, you can train neural networks on pictures of this thing, and this has sunshine and this has no sunshine. But you have to understand that there is a principle, a phenomenon underneath that is causing this. So this is what John was referring to in his paper on the reality. He used to call it phenomenal data mining. The phenomenal data mining, phenomenal data mining was data mining about underlying phenomena. The person at the bottom there, the third one, that is Urea Pearl. He also won the Turing Award in 2011 for the invention and development of probabilistic networks, of Bayesian networks. How many of you are familiar with Bayesian networks? Some of you are, very few. Something to learn about. He said it in a kind of a cutting way, in a way that is a little bit scathing, but it's absolutely right that these dramatic achievements of the network that we see are basically curve fitting. When you train a large neural network on a large amount of data, what you are essentially doing is you are getting this network to learn a function that maps your desired output to the inputs that you are feeding it. This is all that is happening. It is fitting the data that you have and the outcomes that you want on that data to a particular curve on a very large space. And all the great achievements that we have are essentially achievements of getting this curve fitting. It is not about the underlying semantics or the meaning of what is going on in the world. The pictures that you see on the left-hand side are, the bottom one is a page from my own thesis, my PhD thesis, and the one above, I happened to spend a memorable summer at Intel's AI lab. Yes, Intel had an AI lab back in 1990. And the head of the AI lab had asked me to, there were two teams. One was using neural networks to predict. In semiconductor companies, there is a huge problem of loss of semiconductors, especially in the early stages of the manufacturing process. The machines are not particularly accurate, and so the wafers fall off the production line. So you have to detect what is causing the failure. And there was one team that was using neural networks to do this, and it had same thing that we hear now 30 years later. It had deadly accuracy. It used to do a remarkable job of predicting what was wrong by looking at a fallen wafer. But it had absolutely no idea how it was doing that. And then there was another team that had painstakingly built a very large probabilistic network to do the same thing. They had interviewed people and so forth, but this thing was just not accurate enough. It's because even us, when we look at, if you ask a doctor, why do you think this person has the flu or the pneumonia or whatever? They do a great job of diagnosing these diseases, but when you ask people to explain why, even our own explanations are usually not very accurate. And this is because there was a famous tennis coach who used to have this saying that the parts of our brain that play tennis are not the parts that speak English. And Daniel Kahneman, which is the book in the middle, Thinking Fast, Thinking Slow, he won the Nobel Prize in Economics for this work. he had this great observation that intelligent systems like the human brain have these two systems. There is a very fast acting, instinctive, responsive system one. Like if these lights went out all of a sudden, or if there was an earthquake, or if somebody broke that glass, we would all react in a certain way. And that would happen despite whatever it is that we are consciously doing. And this is an example of this fast acting system one. But we also have a slow acting, more thoughtful system two, a more deliberate, more articulate, reflective system two, where stuff that I'm telling you about, you're all listening to it, you're processing it. This is the system that is processing that is the slow acting system two. This is what gives us our judgment, our ability to understand what is going on, make sense of it, and then take actions. And so one of the things that is unfortunate but has to be done is you have to compress these complex thoughts of decades of work by thousands of people into these sound bites and nutshell things. So I have one of these sound bite graphs here at the bottom right. What we have today is a great success in perception and in early stages of understanding. That's the bottom left. And every time you open up a story in New York Times or Wired or what have you, and they talk about superhuman intelligence and terminators and, machines becoming our overlords and stuff like that, it's complete nonsense. Human judgment, human level judgment, human wisdom is very, very, very far away from the work that we are doing right now. And yet, at the same time, if people ask me, how far away, not in my lifetime for sure, not even in your lifetimes, maybe in your children's lifetimes, decades out, possibly a century out or more. We don't even know, we don't even have the techniques to articulate how these things work. There is I'm on the board of BMW, and people in Germany especially, there is all this drama around autonomous driving, and we aren't even close to autonomous driving. I don't know about San Francisco, but down in the valley where I live, every 10th car is one of these mules from, Waymo or Argo AI or all these companies, and these poor slobs are piling up miles after miles after miles, thinking that somehow by looking at every possible road in every possible condition, they'll be able to train these networks. And then you realize that you are in a situation where there is a truck standing in front of you, and there is a double yellow line, and the truck is not moving. What do you do? Did the driver die, or is he out making a delivery? Is it a UPS truck, or do you cross over the double yellow and go around him? We aren't even close to articulating these kinds of situations, and they happen every single time that you drive. And that is my point about human level judgment. We will get to what we will call level 3 autonomy in driving, which is basically with the human still in charge of the car, and the car realizing that I don't understand what is happening, you take over now, and so forth. Some cases in some countries, we will have these small examples of level 4 in the next 10 years, but level 5, which is basically that the car has enough of a judgment to be able to carry you around indiscriminately anywhere. This is not going to happen for the next 50, 60 years, regardless of what Elon Musk says and all of that. So there is a big gap between these two realities, and this reality is progressing quite dramatically, and it is powerful. It is not even close to that reality, but it is incredibly powerful. It is so powerful that it is going to rewire most aspects of society, because in all the perceptual ways, these techniques are already more powerful than our senses. And so what does that mean? What does that mean? What opportunities does that create? But also, what does that mean for the human future? And my own sense is that this is we have to rethink what it means, what skills mean for people given this. So I think all of you are really fortunate that you are already in the data science program. You are on the job creation side. You are on the side of creating these technologies. You are not on the side of the jobs which are likely to be either displaced or transformed because of these technologies. You are the ones creating these technologies. So how should we think about that? What are some lessons that I can point you to? The first one, and they are in increasing order of complexity. The first one is that data science, as you are studying it, is not only about understanding the statistical techniques, the ways to classify and so forth. Yes, you have to do that. That is table stakes, the regressions and the neural networks and all of this stuff. But beyond that, you have to get beyond that. And you have to get beyond that into understanding when we try to use data with these techniques, neural networks or the other techniques, the LGBM or random forest or whatever it is that you guys use, the thing that you are trying to ascertain is my data correct? Are there things that are wrong in it? This requires human judgment. Is the data adequate to forecast the thing that I'm trying to forecast, to classify the thing that I'm trying to do I need more? Our team was recently working on a problem to forecast when ATMs, cash machines, need to be replenished. And it turned out that beyond the data that our customer gave us, you needed data around what day of the week it was. And certain machines that were near this was in Hong Kong, certain machines that were near racetracks had completely different patterns of usage than other machines that were not near racetracks. Certain machines that were in shopping malls had different patterns, depending on what kind of weather was. In the last year, there have been protests, and on days of protest, there was a different pattern. So you have to understand these things, and those things need to go into enriching your data set. So do you have adequate data? The completeness of data, do you have too much data? Are there parts of your data set that are irrelevant to the thing that you are trying to do, etc.? And you have to remember that data is not the activity. The data is the footprints of some activity that happened. So if you go back to the example of the sunrise that I talked about, there is an activity happening, which is the sun is coming up. And that leaves footprints behind, which is the data of the light on these building walls. So there is an activity underneath which creates the data. The data that we look at is the footprints of something that happened. And you have to think about the activity, McCarthy's words, the phenomenon that is leaving this data behind. So don't just look at the data, but try to understand what is going on around and beyond that data. And then you have to go further. You have to think about the outcomes. You have to think about the problem that you are trying to solve, defining the problem. There are many ways of doing this. Most people, we are so fixated on problem solving that we don't think about problem finding. Before we solve a problem, there is someone who articulated the problem. Someone has to define the problem. And turns out that when you have a powerful set of techniques at your hand, these powerful perception, powerful classification techniques, run on incredibly powerful computers, the act of defining the problem becomes crucial. There is a statistic that 85% of data science projects in enterprises fail. And this happens because business people will say, oh, I want to understand why my customers are leaving. So can you build a model to predict customer churn? And then the data scientists build a model to predict customer churn. And then it doesn't work, and it doesn't get deployed or go anywhere. And it happens because people fail to define the problem precisely enough. They fail to come to the same page, and the world of data scientists is so far away from the world of the business people that this bridging of meaning between these groups is not there. So that has to be done. There was a wonderful paper, I forgot where it was, recently, around this customer churn problem, that somebody, um, they've figured out that customers that were at risk of leaving, and then they were given an offer so that they might not leave. Turned out that that act of giving them an offer ended up forcing them to leave far more frequently than they were leaving to begin with. And then people dug into why the hell did that happen? And it happened because many people weren't even aware that they were customers. This thing was just clocking a monthly subscription without people even realizing. And when this offer came in that, hey, if we gave you, this, that, or the other, would you consider not leaving? The guy's like, oh my goodness, I've been paying these people $15 a month and ended up canceling the subscription. So the correct thing to do in this particular case was something along the lines of, who are the customers who have been engaged, who are likely to leave, who would respond to an offer positively. It's a very different way of framing the problem. So this is kind of a strange example, but you know what I mean. The act of defining the problem, what is it that you're trying to achieve? If the machine is going to classify the problem, then we have to step up and step beyond, transcend that situation, and try to define the circumstances around solving this problem. So the outcomes and definition of the problem are incredibly important. When you come into the real world of working on real problems, you will realize that this is an incredibly important skill to have. So one of the things that Dean Caston is working on is bringing this design thinking, problem finding into the engineering curriculum. Exploration and understanding. One of the things that makes me really sad about the state of machine learning is this focus on auto ML. And those of you who are fans of auto ML, I can tell you that techniques, human history shows us that techniques that get us further away from understanding what is going on are never a good thing. They are never a good thing. And this is not a joke. The fact that these deep neural networks are too complex for us to understand, the tools are so horrible that people cannot even tell what kind of a network they have built and why is it better than this other kind of a network and so forth. And therefore the solution to that is that, you know what, we will solve this problem for you. We will tune the hyperparameters. It's complete nonsense. We have to understand what it is that we are building. You have to be able to explain this. And don't let anyone tell you that, oh my goodness, my network had 12 million parameters and therefore how can you possibly explain this? The transistors that people design using design tools have billions of the semiconductors, the devices that we carry around. They routinely have, that the new iPhones have several tens of billions of transistors inside them. And they are all designed on EDA tools which people, using abstraction and using summarization, we understand what is going on. You can verify down to the level of an individual transistor what is happening. We have built nuclear technologies before, and if you look at nuclear technology, nuclear reactors, people talk about Fukushima and Chernobyl and 3 Mile Island and so forth. The number of people who have actually died because of nuclear technology failing is 0. And this is nuclear technology, right? We have a phrase for it. It's nuclear. It's actually nuclear. So exploration and understanding, and the more you explore, what if I try this, what if I try that, what if I tweak this, this is how we learn. So Kahneman wrote about System 1 and System 2. Marvin Minsky, the other father of AI, together with John McCarthy, he wrote this beautiful book in 1985 called The Society of Mind, about how our brain, our mind, is a collection of many different kinds of solvers. And there is this society that comes together as a mind. It is not one thing. It is not one machine. But it is several hundreds of different kinds of things that are formed together in a society. So any intelligent system Even if you look at autonomous driving in the L3 autonomous driving, there are many different solvers inside there that are coming together um, to achieve intelligence. And this building of systems thinking is the counterpoint to design thinking. The ability to understand how we build the systems. And it is a system that you are building. When you use data science to solve a particular problem, you are building a system. You know, when the lunar, when the first time when the lunar craft from Apollo 11 or whatever, was it Apollo 11 or Apollo 13? Apollo 11. Apollo 11, when it landed on the moon, the software system, the people who were landing the plane, the craft at the time on the surface of the moon, actually made a mistake. And they pressed a wrong button. There is a very famous story if you dig it up. And the software system in the lunar craft actually recognized that a mistake has been made by the human operator and overrode that and kept the priorities that were supposed to be high priorities, and prevented the thing from crashing. And actually it landed nicely, and you know, we celebrated as a success and so forth. And the people, and the head of software for that team that did that was Margaret Hamilton, a woman. And people used to tell her that astronauts never make mistakes. You know, what are you talking about? And she was like, I have to design this system. And she said, people used to ask her, what do you do? And she said, I do software engineering. It was the first time that somebody used the phrase software engineering. And she basically said that people will make mistakes. Systems make mistakes all the time. So you have to design the overall system to be aware of the fact that a mistake could happen, bring in the checks and balances inside it, and design it around that. So that overseer kind of a function is incredibly important. And finally, the thing that you have to realize for the foreseeable future, for the rest of your life, it is going to be about humans plus AI. It has to be. There will be things that require our judgment that we have to either program into the systems, or we have to design these systems to be able to interface with us. These things have to become these extraordinary new senses that we have. And unlike this beautiful lunar example from the 1960s, the recent example of the 737 MAX is equally nightmarish. That the autopilot, which was not aware that it is actually flying a plane, or what a plane is, or that there are people inside it, or the plane making contact with the ground is a bad thing, or that it will cause loss of life, and the loss of life is a bad thing. None of these things are inside the autopilot software. And yet it was actually preventing the people from taking control of the plane. This is why those two planes crashed. There was another equally serious, not as malicious example. There was a famous crash of a Air France flight, which was on its way from Brazil to Paris some years ago, I think 10 years ago. Anybody else heard about this story? The plane, because when you go from Brazil to Paris, you cross over the equator, and it's warm air there, and so at very high altitudes there are frozen clouds because of a unique phenomenon that happens around the equator, because at the surface level the air is warm and so forth. So it's a frozen cloud. So the plane flew through a frozen cloud, and it has this instrument called the pitot tube, which measures the speed of the plane. And the plane is peacefully flying on autopilot. You know, other than the 7 or 8 minutes at the beginning and the end of a flight, the plane these days basically fly by themselves. And so this thing flies through this cloud, the pitot tube stops functioning, and the autopilot disengaged and handed the control back to the pilot. So you fly this thing. No explanation, no nothing serious has happened, just the pitot tube has stopped functioning. So I don't know how fast we are going, and so therefore you fly it. Even that level of communication did not happen. It just released the control, and so this kid, the youngest of the crew, was flying the plane at the time, and he completely panicked, and the the second senior guy was also in the cockpit. He said, "What happened?" I said, "The autopilot gave me back the control." So he said, "Go get the pilot." The main pilot was sleeping because of a long flight. He was on rest. So by the time the main pilot had flown for several thousands of hours, and by the time this main pilot comes into the cockpit, there is complete confusion around what is going on in the plane. It's nighttime, and so the main pilot, when he understood what was happening, applied his judgment, actually came to the right conclusion that the plane had gone into a stall, and they thought that they were diving, and so they tried to raise the plane, and so then the plane was going up like this and got into a stall and so forth. He said he gave the right instruction, but the two pilots were executing opposite instructions at the same time. Anyway, long story short, within 4 minutes, the plane was in the water, everybody died. And it happened at its root. There is a very nice book about this called Our Robots, Ourselves, that you should read if you get a chance. It's an example of a bad interface between the human and the machine. There was another Lufthansa plane that flew by basically the same spot at basically the same time. Nothing happened to it. It flew through the same cloud as well. It was a completely minor thing that should have been very insignificant. But this, and now we are talking about, there are 3,000 companies that I mentioned who are building AI systems. And heaven forbid if these systems are in charge of something serious, The test trial of the Uber in Phoenix, which ended up killing this person, was one thing, but I am not at all convinced that we are training people enough on the integration between our interfaces, our judgment, our sense-making ability with this AI. But I think as you think about data science, you have to look into this particular dimension of it. And most important, of course, is teaching. My wife is on the board of Code.org, which is in charge of, it's one of the non-profits that looks into computing literacy, bringing more people into the world of coding. It's a shocking situation. She has this statistic that back in the dark ages, something like 6% of the world's population could read and write, were literate. Now that number is like 87% or something. And today, the number of people who can program a computer is about 35 million, which is about 0.5%. So when the dark ages were transitioning to the Middle Ages, we had more people who were literate than we have computer literacy today. And then out of that 35 million people, if you look into how many people can program, do data science systems, can use deep neural networks or regression or light gradient boost or whatever to do something, that number is like 500,000. Out of 7 billion people in the world, 500,000 can build you an AI application or a data science application. And out of those 500,000, roughly 25,000 could actually explain to you the underlying techniques of the thing. The remaining ones just use TensorFlow or PyTorch or whatever to build something without actually understanding the underlying techniques to the point of being able to explain this. Now this wire fell down and I hope nothing bad has happened. Make sense? Everybody with me so far? This teaching thing is particularly important. I think if you look at the job situation, you should probably know this. This is not scientific fact, this is my estimation. I came up with this coefficient because my name begins with V, I call it the V coefficient. Also, my company's name begins with V for the same reason. So if you look at the ratio of how quickly education and training are able to create the skills for the next generation kinds of jobs. meaning the supply of the people who can perform the next generation kinds of jobs, and you look at the rate at which automation technologies are displacing the current jobs, there are three possibilities. One is that this ratio is less than 1, which means that automation creates more displacement than we are able to create jobs which are able to transcend that displacement. Then all this nightmare, Yuval Harari's book on this useless class and all these things then come true. If this constant stays more or less 1, then this is basically a steady state. This is kind of where we have been since the Industrial Revolution. People used to talk about job displacement in the Industrial Revolution. Oh my God, these massive machines, the loom, the steam loom, the steam engine, all these things are going to displace jobs. And of course they did. About 100 years ago, at the turn of the previous century, roughly 96 or 97% of the country of the US was working in agriculture one way or the other. Now it is less than 1%. And we have no shortage of food. We have, in fact, an obesity epidemic. And we have less unemployment than we did back then. So this constant has basically been 1 so far. And now it looks like, if you look at Kai-Fu's prediction and all the other statistics that I showed you earlier, it looks like there is, for the first time, there is a danger of this going away. And of course, if we are able to exceed 1 on this front, then we have a real hope. Then we could really transcend these technologies and turn them into things that improve us. So what does my company do after being involved in leading 2 very large companies? One as the head of products and member of the board, the other as CEO. I looked at all of this stuff and I thought that I want to build a company that does something about this. And how many times in life do you get an opportunity to do what you really feel like doing? So that's what I do. The company is called YNI. We are building a platform to make it easy for enterprises to build AI systems. To not only build AI systems, to dramatically increase this number from 500,000 to at least to 35 million programmers. Every programmer should be able to build this. In fact, beyond programmers, anybody who understands basic math should be able to build an AI system. And not only build an AI system, but build an AI system that you can explore, that you can deeply explain what is going on inside every aspect of it. You have to be able to build a system like that. And that's the platform. Aslian is here. She is a part of this platform team. We also do consulting services, design-led consulting services for CEOs and so forth. We have some applications, and we are working on education. You'll hear more about that in the next couple of months. So that is my company. So in conclusion, this is a picture of basically of the history of our planet on the geological time scale. The interesting thing here is this giant pink area. I mean, you know, my wife always reminds me that men are not particularly good at color, so I think that is pink, but it might be fuchsia or lavender or whatever. That big thing in between. There is only one big thing in between, guys. That was the Cambrian Explosion. Anybody here know about the Cambrian Explosion? You hear a lot about the Cambrian Explosion in biotech, or Cambrian Explosion in mobile, or Cambrian Explosion in AI, but this is the real Cambrian Explosion. About 500 million years ago, something happened that created the largest diversity of life on the planet. And only recently, scientists have been able to figure out what it was. It turned out that back then, we are talking about 500 million years ago, the Earth was basically covered with water. It was highly toxic by today's standards. Life was all underwater. And around this time, for the first time, there was enough oxygen in the atmosphere that it became possible to breathe. And And so life started to come out of the water and develop the ability to live outside water. Outside water, there was also light, the sun. And in water, it is dark. The moment, basically within a few feet, it gets really dark. And so, all these species developed the ability to see. So they got eyes, and eyes in the front, and eyes in the back, and eyes on top, and 100 eyes, and 1,000 eyes, and eyes in the knees and elbows, and all kinds of eyes. So the Cambrian explosion, it turns out, was about the ability to see, because it gave people, for the first time, the ability to thrive and not be hunted and be the hunter and all of those things in the light. And when I think about the future, yes, human judgment is very, very far away. But the time of AI, the time of these powerful data science techniques, is really the time to develop the ability to see one more time. It is the act of building something new, the act of innovating, is the act of seeing something that is not there. Everything new that you see around you was built by someone who saw something that did not exist. The world was missing that thing. It's a different kind of an ability. That our eyes are programmed by nature to see what is there. We are not programmed to see what is missing. And invention is the act of seeing something that is not there. So Alan has a wonderful way to say it. He calls it the best way to predict the future is to invent it. I think that if we do it the right way, AI can end up being a great amplifier for us. Our burden is going to be able to look out there and see what is not there and define that unknown, and then use AI to help make that happen. We are, in your lifetimes, we are going to get to a situation where things that you can precisely articulate will be done better by machines. This is going to happen. But the burden of articulating those conditions, articulating those problems, those things to work on, that burden is on us. So in other words, what happens to this V constant is up to us. Thank you very much.
So we have questions? A couple questions? Hi, I'm one of the students in the master's program. First of all, I wanted to thank you for your talk. It was really interesting, especially in conjunction to a lot of the classes that we've taken so far. I have two questions, if you don't mind. The first one is actually, is there a series or list of all the books that you mentioned? You mentioned quite a few in your talk that maybe after the program's done, I have a little bit more time to read. I'd love to actually read.
Sure. I have to look back on which ones I actually mentioned, and then I do have a reading list that I give to our employees when they join the company. But I will, Kim, I will dig that up and I'll send that out. Yeah.
The second question had to do with you're referring to even the middle where you're talking about the difference between perception and mild understanding versus strong understanding.
Judgment, yeah.
And human judgment. I know right now we're kind of at the point in the type of machine learning that we're doing where it would be hard for us to really understand how we would achieve that. But do you have any thoughts or maybe guesses as to how we would come about something like that?
There are many things that people are trying. You know, I mentioned the 3 Turing Award winners, Hinton and LaCoon and Bengio. Even they realize that there is need for deeper kinds of reasoning and more modular architectures and so forth. The difference right now is that there is a school of thought that is emerging, which is that these large neural networks will develop these abilities to create structures and create meaning, create reasoning the Facebook guys did a arithmetic engine, something that a neural engine that can do simple arithmetic strictly by using these connectionists, these neural network type techniques and so forth. So there is that school of thought. There is another school of thought that is working on larger architectures. Um, Josh Tenenbaum at MIT is one of the proponents of that way of working. Murray Shanahan is in Imperial College London. He works on that stuff. My own thesis was in that area, which is that you have this kind of a symbolic system too, based on theorem proving or explicit representation of knowledge that surrounds a lot of individual um, specialists like neural network systems and so forth. Um, there might be other things that emerge and so on. But I think that clearly the ability to represent knowledge, to communicate knowledge, to reason about knowledge, both introspectively as well as in communication with other agents, that is, without that, this stuff is not going to happen. And we still are not close to that. Um, and then to be able to take actions to do that effectively is still a long journey ahead. Um, if you just look at the power consumption situation, it is quite extraordinary. Um, I'll give you two statistics. So we have about roughly 10 billion neurons. First of all, counting the number of neurons and all that is a completely stupid and wasteful exercise, because it has nothing to do with 10 billion neurons. We can do a lot more and so on. But just from a power consumption perspective, for the sake of a closer apples to, it may not be apples to apples, but it's more like apples to mushrooms or whatever. But it's not apples to trucks comparison. So with 10 billion neurons, we have about 100 trillion synapses. So the connectivity of the neurons is ridiculously higher in our brains than in the neural networks that we build today. We basically process things through these 100 trillion neurons in about 2,000 calories a day. So even if you assume that all 2,000 calories that we eat go into the brain, which they don't, but let's say for the sake of argument that all 2,000 are going into the brain. So for 2,000 calories, which is, 4 donuts or whatever, we can calculate with 100 trillion synapses. And the equivalent, just information processing, is 8 orders of magnitude less efficient today. It's 100 million times less efficient. So DARPA had a proposal 2 years ago to bring this down by 10,000 times. So improve the power efficiency of doing calculations by 10,000 times, which would still leave it 5 orders or 4 orders below where we are. So I think that these things are still, you should have this thing that autonomous driving, I mean, the fact that every car company CEO basically showed up between 2015 and 2017 and said that we'll have autonomous cars by 2020. And here we are in 2020, they are not even close. It's unbelievable, The so I think there is still a long journey ahead. The Japanese are particularly good at making robots, and probably as a country, the furthest ahead in robotic technology. And then they have to be, because they face a very acute aging crisis. The population of Japan is becoming older at an alarming rate, and they don't have people to take care of the elder. And I asked one of my friends who is a leading roboticist, and he said that, the packing of a bento box, like basically if you walked into a Japanese kitchen at lunchtime, there are all these people that pack the bento boxes and hand those to you very quickly. We are 10 years away from a robot that could pack a bento box. And, the Japanese would love for there to be robots that could pack a bento box. Nobody will miss packing bento boxes. But in this decade, a robot that could assemble a bento box is not going to happen. So. Yeah, Jeremy. You're absolutely right. It is a marketing thing, and I think it requires that people. There aren't that many people from our generation who studied that and were around then, and the burden falls on us to some degree to correct these kinds of perceptions and give people examples. I showed you the example of the BERT-based neural networks for language processing. Terry Winograd saw several waves of these AI hypes over the last 50, 60 years, and he came up with these Winograd schemas. Some of you who study natural language might have heard about Winograd schemas. They are sentences like, Joe crossed the school bus because he was driving too slow, and Joe crossed the school bus because he was driving too fast. And these two sentences are entirely different. In one case, the he refers to Joe, and in the other case, the he refers to the driver of the school bus. And you didn't need a second to figure that out, and none of the systems that I showed you can do this kind of a thing. Because you have to have an understanding that school bus, there is a driver, school buses are conservative, the Joe decided to cross the bus, and so because the bus was going too slow. And that um, you have to have the ability to build this kind of knowledge about the world, to reason about this knowledge about the world, apply it to the current situation that you are perceiving, and then take an action based on that. So all these things have to happen before we get to a better design of AI systems. Yeah.
Hello.
Oh,
Um,
where are you? Oh,
okay.
yeah.
In the skills coefficient slide, you mentioned losing jobs to automation and how we can balance that by creating other jobs. Do you think that loss in jobs can be completely balanced just by new jobs related to AI, or do you think there's like universal basic income type things that the government also needs to enact?
Um, First of all, I think, the basic answer to your question is I don't know. But my personal belief is that, so it is not just the AI related jobs. You may not need the equal number of AI related jobs, just like the agriculture example shows us. But I think that clearly there are enough ways that we can transcend the AI instead of becoming irrelevant as a result of AI. That new kinds of skills, new kinds of jobs that leverage those things in unimaginably new ways can be done. I personally, um, there are days when I wake up and I think that maybe I am wrong, but by and large, I am optimistic that there is enough in human imagination that if we can sort of unleash this kind of an imaginative um, a revolution of imagination, the Cambrian Explosion that I talked about, that we can create entrepreneurs by the billion. And today we are sort of in this time where, Wired magazine or TechCrunch will write about a Mark Zuckerberg or a Steve Jobs that, oh, they were inventors. And if you look at a 4-year-old child, they never stop asking why. We basically beat that out of them. They always ask why. They annoy the hell out of you by asking why. Why is that? Why is this happening? And then you give an explanation, and then they say, oh, but why is that? So if instead of sort of pushing them down and burdening them with so much crappy homework from 100-year-old textbooks, I mean, seriously, if you look at when was the last time the physics textbook was updated? It's more because the teachers don't know any better that we keep the system the way it is um, than any other reason. There is no reason why students cannot learn about all that has happened in physics since the days of Isaac Newton, and yet our books are basically about that. Um, so I think that curiosity and imagination are an inherent ability that we have. Every time I take people through a design thinking class, it suddenly they realize that, oh man, I can look at this thing and I can ask myself how to improve this and so forth. So people of course say that, what are you talking about? How can there be a billion entrepreneurs and so forth? And I personally happen to think that we can. If we cannot, and if for whatever reason we are not able to do this, then you end up in a situation like universal basic income and all of that. But so one part of your answer is who knows. The other part is I think it is definitely possible for there to be a situation where we are in command of this stuff.
Andrew mentioned that he used to read every paper that would come out about machine learning and
It is impossible now. It's 80 a day. On archive, there are 80 papers a day on the machine learning category. So
How important is it to keep up with the latest research, and how do you do it?
the leave enough room to follow things that you believe are of high quality and so forth, because I think that you can do. And then also leave enough room to see that maybe you are wrong and to change your beliefs and so forth, because if you only do the former, then you risk becoming insulated into the kinds of people that you agree with. Um, so I think something like that, being able to very quickly judge what is of good quality and what is not, and staying open to that is important. It is back when I was a student, you could keep up with the field by going to the conferences, reading the journal papers, and so forth. This is not possible anymore today. Um, but I think that you can, by and large, find out the deeper people who sort of scratch the surface of things, and then following those. That's a good problem to solve, by the way. You know, John H. Mendy, one of my PhD advisors, used to say that when you don't understand the problem, then defining the problem becomes the first problem. So you have to ask yourself, how do you keep up with the field honestly at a time of 80 papers a day?